now we're going to look at neutralization reactions in light of what we discussed before. So we discussed acids and bases, strong acids and strong bases. And I think we talked about acids earlier in chapter 2 or 3, I don't remember. But in any case, we talked about the fact that acids have certain properties and bases have certain properties. And what we're going to look at is a reaction where you have acids reacting with bases, and as a result of the reaction, the products that they produce will cancel out each other. And we call this a neutralization reaction. All right. So I'm going to use a simple example to illustrate what happens in a neutralization reaction. So the example that is shown here is the reaction between hydrochloric acid and potassium hydroxide. And you can predict the formula for the resulting products because one of the products will be water, which is formed as a result of the hydrogen from the acid coming together with the hydroxide to form water. And then the other parts, the potassium, come together with the chloride to form the salt, which is the other product. And the salt in this case is known as potassium chloride. All right. And as stated here, we can use what are known as acid-base indicators to tell whether or not a reaction goes completion. We'll talk about that later on. Okay, so that's basically an example of the neutralization reaction. And just to be sure, excuse me, that we understand what happens, I'm going to use another example. So let's say we have a reaction between sulfuric acid and let's say barium hydroxide. I'm just choosing these two. So again, what will happen is that the barium, in this case, from the base, will come together with the sulfate to form barium sulfate. And the hydroxide will come together with the hydrogen to form water. And in this case, we need to make sure that the equation is balanced. And in order to balance this, we need a 2 here. And that will take care of that. All right? So that's basically what happens in these reactions. Okay, so what we're going to look at is how do we get what is called the net ionic equation. And this is basically the equation which represents what actually happens in reactions such as neutralization reactions, right? Now, in order for us to determine the net ionic equation, we need to determine what are known as the spectator ions. And the spectator ions are basically those ions that exist in the equation on both sides in the same state. In other words, basically they remain unchanged as you go from reactants to products, all right? Now, the other substances involved would be the actual participants in the reaction, and therefore these are directly involved in the net ionic equation. All right, now in order for us to determine the ions to begin with, we have to determine which species that are in or represented in the equation will exist as ions in the aqueous solution. So the example we're going to look at, again, is the example of hydrochloric acid with potassium hydroxide reacting to form the products as we said before. Now, if you recall, we said that hydrochloric acid is a strong acid, potassium hydroxide is a strong base. So they will both undergo complete dissociation, right? Potassium chloride is an ionic compound which is in an aqueous solution, and therefore that will also undergo complete dissociation. Any ionic compound that exists in aqueous solution will undergo complete dissociation. So therefore this will split up, the hydrochloric acid will split up to form the ions. The same will be true for potassium hydroxide, the same will be true for potassium chloride. That will not be true for water because water is a molecular compound. As a molecular compound, it will not split up to form the ions. So we can represent this equation here, which we call, in some textbooks, they call this a molecular equation or the molecular equation, which, to be perfectly honest, is a bit of a misnomer because not all the species involved are molecules, but that's a terminology that is applied to an equation such as this. And we can rewrite this as what we call an ionic equation, where we show explicitly all the ions that are formed in the aqueous solution on both sides. So the hydrochloric acid will split up to form H plus and Cl minus. The potassium hydroxide will split up to form K plus and OH minus. The water will remain intact because it's molecular, and the potassium chloride will split up to form potassium and chloride ions. And at this stage, we can, oh, by the way, this is called the Ionic equation. So let me, hold on 1 minute. Let me write down, where should I put that? Let me put it here. So this is called the Ionic equation, all right? So at this point, we can identify the spectator ions because as we said before, the spectator ions are those that remain unchanged on both sides of the equation, and more specifically, the Ionic equation. So if you look at this equation here, you'll notice that there are two things that are the same on both sides. You have the chloride ions, which exist on both sides, so we can cancel them out. And we also have the potassium ions, which are the same on both sides, and we can cancel those out. All right? So therefore, from this Ionic equation, after canceling out these ions on both sides, we're going to be left with the net ionic equation, which is simply the H plus reacting with the OH minus to form H2O. All right? And that's basically how we get the net ionic equation from the molecular equation for this reaction between hydrochloric acid and potassium hydroxide. Okay, so now that we have covered that, I'm just going to say a few words about titration because this is something that is actually done in the lab. Titration basically is a technique that is used to determine more often the concentration of one reactant in a solution using another reactant in another solution. All right. And in order for you to do that, you need to know the concentration of the reactant in the solution that you're using to find the concentration of the other solution. So basically, one reactant or one reactant solution is placed in a piece of glassware known as a burette. The burette is a long cylindrical piece of glassware. If you're going to do lab with me, you'll definitely be introduced to this piece of glassware. And the other reactant is placed in a flask with a few drops of an indicator. And the indicator, as the term suggests, indicate the point at which you add enough reactant from the burette into the reactant in the flask such that the reaction is complete where both reactants are completely used up. All right. So the reactant that is in the burette is called the titrant, and it is slowly added to the reactant in the flask until the indicator changes color, and then you stop adding your reactant, and based on the amount of reactant added, based on the amount of the concentration of the reactant in the burette, and based on the amount or the volume, I should say, of the other reactant in the flask, you can determine the concentration of the reactant in the flask. And that's pretty much all I'm going to say about that because we're going to discuss that in more detail during the lab. Okay, one other thing I want to talk about here. Well, actually, some other things I want to talk about here. There are some acid-base reactions that form gases as products, right? And these are the examples of these reactions, right? So I'm just going to go through these very quickly. So if you have an ionic compound which contains either the bicarbonate or carbonate ions, if you add acid to it, now these will act as a base, right? The carbonate ion and the bicarbonate ion will be acting as bases. In either case, when you add acid to them, and acid of course will contain the H plus ions, then the products of these reactions will always be CO2 and H2O. And a demonstration of that is shown here in this picture. So what this person here is doing is squeezing lemon juice onto sodium bicarbonate, which contains a bicarbonate ion. The lemon juice contains an acid known as citric acid, which provides the H plus ion. So basically, if you were to do this reaction, and you can do this at home, and you can also use vinegar instead of lemon juice because vinegar contains an acid as well, contains acetic acid, which does the same thing. What you'll observe is bubbles being formed, right? And the bubbles being formed would be due to this gas, carbon dioxide, all right? So that's an example of an acid-base reaction forming a gas. In this case, the gas is carbon dioxide, and that will be formed when you add anything acidic to any compound which contains the bicarbonate or the carbonate ion. Now, the other two reactions here, where you have either the bisulfite or sulfide ion, if you add acid to any compound containing these ions, you're going to end up with water and a gas known as sulfur dioxide. Now, the thing about this reaction is that this reaction, I would not recommend you do at home, unlike the previous one, because the SO2 gas is a very, it's poisonous, but it's also choking. In other words, if you're in a room filled with this gas, you start coughing and find it difficult to breathe and all of that. So this is something I would not recommend that you do at home. All right. And then the last two ions, the hydrogen sulfide and the sulfide ions, um, any compound which contains these ions, if you add acid to them, will produce hydrogen sulfide gas. Now, the thing about this reaction here is that I definitely would not recommend that you do this at home. Because for one, the gas that is formed is very awful smelling, has a smell of rotten eggs. In fact, the odor of rotten eggs is due to the formation of hydrogen sulfide when the albumin in eggs, which is a protein, undergoes decomposition. All right. And in addition to the fact that the gas is awful smelling, it is also toxic as well. If you're in a room filled with this gas and you breathe it in and it builds up to a certain level in your blood, it will kill you. All right. So this is something that I would not recommend that you do at home. But this is also another example of an acid-base reaction which generates a gas. So these are a group of reactions that you need to remember when it comes to acids reacting with any one of these compounds containing any one of these anions. Okay, the last set of reactions I want to talk about are precipitation reactions. And these are reactions where you have two clear solutions containing ionic compounds, and then when you mix them together, it forms spontaneously a solid. And I think the example that is shown here is the reaction between lead 2 nitrate. Let's see, where can I write this down? Whoops. Okay, so lead 2 nitrate, which is in an aqueous solution, plus potassium iodide, which is also in an aqueous solution, to form lead 2 iodide, which is a solid, plus potassium nitrate, which is an aqueous solution. All right? And of course, we have to ensure that this equation is balanced. So we're going to need a 2 here and a 2 here. So now the equation is balanced. All right? So this is the reaction that is shown here. The pale yellow solid that is formed here is due to the lead 2 iodide that is formed, right? So what this person did, and I'm not sure which one of these was in a test tube, but it doesn't matter. So let's say the potassium iodide was in a test tube initially, and then this person decided to add drops of lead 2 nitrate to it. Upon contact with the solution, the lead 2 nitrate would form lead 2 iodide when it reacts with the potassium iodide. And that's why we see and observe this solid here. Okay, now, in order to make sure that we can tell accurately when or if a reaction of this type will take place, we have to be able to predict whether or not a precipitate is formed, because one could predict what the products are based on double displacement reactions where you have an exchange of ions, right? So anyone could have predicted that, okay, lead 2 iodide will be formed and potassium nitrate will be formed as a result of exchanging ions. The problem is, how would you be able to tell whether or not lead 2 iodide would be the precipitate or lead or potassium nitrate would be the precipitate, right? Now, in order for us to do that, we have to use solubility rules. And the next slide gives you my version, or the version that I prefer, of the solubility rules, which you can use to make predictions about precipitation reactions, right? So this chart you'll have access to in order to make such predictions. So for example, just to show you what kind of information you can get from this chart, let's look at the first line, which says that almost all nitrates, acetates, perchlorates, group 1A metals, and ammonium salts are soluble, right? So any compound, any ionic compound that fits the description of that first line, you can tell that that would be soluble, that compound would be soluble. Then we have the next line which says most chloride, bromides, and iodides are soluble, but there's certain exceptions. And those are lead 2 plus and silver plus and mercury 1, all right? So any compound that fits this description would be soluble, but of course you need to note the exceptions to that particular line, all right? And of course you see some other descriptions about other types of compounds as to whether or not they'll be soluble or insoluble. So you can use this as a guide to make predictions as to whether or not a precipitation reaction will take place. So for example, let me rewrite the equation I had on the previous slide down here. So the reaction is PbNO3 2. What I'm going to do is rewrite these without the state symbols. Potassium iodide, and then arrow, and then lead 2 iodide plus potassium nitrate. All right? So let's say you're given this reaction or this equation, and you're asked to make a prediction as to whether or not a precipitation will occur. Well, firstly, the lead nitrate here has a nitrate ion, and based on the first line here, all nitrates are soluble. So therefore, we can put AQ here to indicate that this would be in an aqueous solution. Potassium iodide. Potassium belongs to group 1A. So therefore, any compound which contains potassium will be soluble. So therefore, we can put AQ here as well. All right? Then we get to lead 2 iodide, right? And it says most chlorides, bromides, and iodides are soluble. But look at this. The exception would be lead 2 plus, right? So lead 2 iodide would be insoluble, so therefore this will exist in a solid state. And then finally, potassium nitrate, we know it's going to be soluble because 1, it's a nitrate, and 2, potassium belongs to group 1A. Excuse me, so therefore we know that potassium nitrate is soluble, so therefore we're going to put AQ here, right? So that's how we can predict whether or not a precipitation will occur, because in this case here, we have 2 aqueous solutions coming together, reacting with each other to form a solid, right? Which would be lead 2 iodide, all right? And again, this is what we call a molecular equation, all right? Again, this is a bit of a misnomer because in this case, there are no molecules, but that's a terminology that is used for this type of equation. So what we're going to look at now is how do we determine the net ionic equation based on this molecular equation. So let me create a new PowerPoint document so that I can have something to work with, so as to show you how to get a molecular equation. Well, the net ionic equation from a precipitation reaction. All right. So again, I'm going to rewrite the reaction, the equation for the reaction between lead 2 nitrate and potassium iodide. So PbNO3 2 aqueous plus Ki solid, and that should be 2. I'm sorry, aqueous. This should be aqueous to give PbI2 solid plus 2 KNO3 aqueous. Okay, so that's the molecular equation. So let me write here molecular equation. Okay, so the net ionic equation is what we're trying to get. So before we do that, before we get to that, I'm going to figure out what the ionic equation is. And if you remember, when we were looking at the neutralization reaction, we determined that any ionic compound that is in an aqueous solution will dissociate to form ions, right? So this is in an aqueous solution, that's in an aqueous solution, and this is in an aqueous solution. So therefore, they will dissociate completely to form ions. So the lead 2 nitrate will dissociate to form Pb 2 plus aqueous plus, and then for the nitrate, 2NO3 minus aqueous. And the reason why we have a 2 here is because we have a 2 here as a subscript, right? And then we have 2 potassium iodide aqueous. The potassium iodide will dissociate to form 2K plus aqueous plus 2I minus aqueous. All right? So that takes care of things on the left side. And then on the right side, the lead iodide, the lead 2 iodide is a solid. So that will not dissociate. So we're going to leave that as it is, PbI2 solid. But the potassium nitrate, that will break up. There are 2 of them. So therefore, that would form 2K plus aqueous plus 2NO3 minus aqueous. All right? So that would be the ionic equation. And if you recall, when we were looking at getting the net ionic equation for the acid-base reaction, the neutralization reaction, what we did is that we cancel out the spectator ions. Remember, the spectator ions are those ions that remain unchanged as you go from left to right. So they are identical on both sides. So in this case, we can easily identify the spectator ions. That would be the nitrates here and here, and that would be the potassiums here and here. So therefore, what are we left with? We're left with Pb2 plus aqueous plus 2I minus aqueous to form Pb I2 solid. And that would be the final answer in terms of the net ionic equation. All right? Okay, so that's basically how we determine that. That's a typical type of question in your future test exams, whatever. Okay, I just want to show you this slide. I think this is going to be the last slide for this topic here. These are just a couple of examples of applications of the type of reactions we just talked about, precipitation reactions. And I'm not going to go through all of them. I'm just going to highlight a couple of them, such as the first one, where this one is used to basically reduce the amount of hydroxide ions present in water. So it's used as a water purification type reaction. Basically, the precipitate formed is aluminum hydroxide. It's a kind of gelatinous precipitate, which can be removed easily after you add the aluminum ions present, to the hydroxide ions that may be present. Just another example here, magnesium can be added to seawater to remove hydroxide ions, or I should say the hydroxide ions is added to seawater to remove the magnesium ions, which forms a solid, and that can be, of course, removed as well. This is using photography, the formation of silver bromide as a result of the reaction between silver ions and bromides. So these are all examples of applications of precipitation reactions. Okay, we're going to stop here, and then the next video I'm going to post up will be dealing with redox reactions. All right? Okay, until next time.